In the previous two lectures, we have seen actually the basic fundamentals to study the concept of central forces. In this regard, you have seen the expression for velocity and acceleration in plane polar coordinate system, because we know that the study of central forces become more convenient when we use the uh, plane polar coordinate system. So, in the previous two lectures, we have discussed all those basic fundamentals. Now, from today, we are going to start our actual topic, that is the motion under central force field. And so, in this first lecture on the central force field, first of all, we will define what is this central force, because we have to study the motion under central forces. So it is necessary to know how we can define a central force. So in this lecture we will only see the definition of this central force and a few examples to clarify the definition of central force. And for this, let us see this figure. I have actually considered here a coordinate system with the x, y and z axis having origin at point O. And let us suppose that at a point P, you can see this figure, there is a particle of mass m0. So this particle of mass m0 is situated at a point P. And with respect to the origin of this coordinate system, the position vector of this point P I have taken here r. So you can say that this vector OP is equal to r, which is actually the radius vector or the position vector of the point P, where you have assumed that the point mass m0 is located with respect to the arbitrary origin. Now let us consider that a force is acting on this point mass m0, which is situated at point P. The force F, if the force F is acting on it, that force will be called a central force only when two conditions will be satisfied. The first condition is that the force F acting on this point mass m0 should be directed towards a fixed point. Let us say O. Here O is origin, but don't confuse that this must be origin. This is an arbitrary point. And if you consider that the force acting on this m0 is directed towards this point O, as I have shown here by this arrowhead, that this force is directed towards the point O. Or if it is directed away from the point O, it means the force acting on the point mass m0 is directed either towards O or away from it. Okay? This is the first condition. And the magnitude of this force acting on m0 depends only on this r, that is the distance of the point P or m0 from this fixed point O. On that distance r, the magnitude of F depends. So if these two conditions are satisfied by the force F, then we call this force as a central force. Okay? I have actually mentioned it here. You can see, for your convenience, I have supposed that F is a force acting on a particle of mass m0, and this force is such that it is always directed from m0 toward or away from a fixed point O. This is the first criteria. And at the same time, the magnitude of this force depends only on the distance OP equal to r from O. In fact, if the force acting on m0 F satisfies these two conditions, again you can see that I have told that the force F should be directed either towards the point O or away from it, and its magnitude is only a function of r, where r is the distance of point P where m0 is located from the point O O, where in which direction the force is acting or away from which the force is acting. In that condition, as I have told you, that this force will be called a central force. And the fixed point O, see the figure. This fixed point O, either towards which the force is acting or away from which the force acts, that particular point O is called center of this force. It means the point towards which the force F acting on m0 is acting or away from which this force is acting, that particular point is called center of force. Okay. So satisfying these two criteria, if you want to express this central force in symbol, so in symbol you can express that if F is the central force, then it is denoted as F equal to F of R times R hat. F of R times R hat. Or you can say that this is F of R times R over modulus of R, mod of R. Okay. In fact, here this F of R, this represents the magnitude of F. This is magnitude of F. And in argument I have written R, which indicates that the magnitude of this force F should be only a function of R. It should depend only on R. Okay. And this R hat is actually a unit vector, and this is in the direction of the vector R. So you can say that R hat is a unit vector in the direction of vector R. Okay. This is also called a radial unit vector, as you have learnt in the previous lectures. Okay. And this unit vector is defined by this expression, vector R divided by mod of R. You know it. Okay. Now, this central force acting on this particle m0 may be either attractive or it may be repulsive. Okay. And that completely depends on the value of this F of R. So there may be two situations. First of all, you can see that if this F of R, which is actually the value of force F, if it is less than 0, that is, you can say that this F of R is negative. In that condition, the force acts toward the point O. If F of R will be negative, that means the force is acting towards the fixed point O, and then you say that the force is attractive. Then what will be the force? Force will be attractive. Okay. But if this F of R, this is greater than 0. When you say that F of R is greater than 0, that means F of R is positive. In fact, in that condition, the force acts away from O. This arrowhead I have shown here, that the force is acting away from O. And in that condition, this force is repulsive. Force is repulsive. So central force may be attractive or may be repulsive. In case of attractive central force, actually this force acts in the decreasing direction of R. It tends to decrease R. While in case of repulsive force, it tends in the increasing direction of R. In other words, you can say that the attractive central force is acting in the opposite direction of radial unit vector, and the repulsive central force acts in the direction of the radial unit vector. Okay. And this fact I have also mentioned here for your convenience. You can see that I have mentioned it, that in symbol F is a central force if I double F. It means if and only if. It means the necessary and the sufficient condition for F to be a central force is what? this must be expressed as F equal to F of r times r hat, where r hat is equal to vector r by r, that where r is actually modulus of vector r. Okay, and as I have told you that this r hat is a unit vector in the direction of vector r. Okay, symbolically we denote the central force by this symbol. And again I have told you that this central force may be attractive or may be repulsive. All these things which I have just explained, I have mentioned it here for your convenience. You can write down these things in your notebook, and that will be a good note for you. And so you can see, if f of r is less than 0, that is f of r is negative, then the central force acts towards O and it is attractive. Okay, I have already explained it. And just opposite, if f of r is greater than 0, or you say that f of r is positive, then the central force acts away from O. Remark it, away from O, and then it is actually a repulsive central force. So this was a simple definition of central forces, and I hope you have understand how the central force will be defined. Okay, only there is two things. This force always acts either towards a fixed point or away from the fixed point, and its magnitude depends only on the distance of the point of action of the force from the point where, in which direction it is either directed or from which it is directed away. Okay. Now we will illustrate this definition of central force by taking two important examples. In first example, I have taken gravitational force. You know, this gravitational force is a very important example of central force, and in fact in the forthcoming lectures we will mainly concentrate in classical mechanics motion under this gravitational force. When you deal with the planetary motion, that motion is under a central force, and what is the central force there? There is the central force which is gravitational force. Okay, so this gravitational force is a very important and very familiar example of central force. Now you can see that how we can say that gravitational force is a central force. For this, let us consider that at this point P, where we have assumed in definition there is a point mass m0, and there is another mass, let us say m, at the point O. Okay, and the position vector of this point P with respect to O, I have assumed r. In other words, you can say that the distance between the point mass m and the point mass m0 is equal to r. Okay. Now you have definitely studied gravitational force. This force is always attractive. It is never repulsive. And this gravitational force can be found by using the Newton's law of universal gravitation. So using Newton's law of gravitation, Newton's law of universal gravitation, you can find what will be the gravitational force acting on this point mass m0 due to this m. So write the expression. This is a very simple expression and you all know it. So gravitational force on m0 due to m situated at O. Situated at O. And this force, you know, this is given as minus gmm0 over r square times r hat, because you know this force is attractive, and if you consider that the radial unit vector is r hat, then this force actually acts in the negative direction of this radial unit vector r hat. I have actually shown it here in the separate figure, and so this force is directed in the direction of minus r hat. Okay, and so you can see we can equivalently write this expression like this. This is minus g mm naught over r square times r over r. Okay, instead of r hat we have written vector r by modulus of r, and you can also see that this f is equal to minus g mm naught over r cube and times r. Okay, and so you can see here that this f can be expressed by this expression. This f is equal to f of r times, sorry, the page has been turned. This is just a drawback of this device, and it will be just okay, so don't be worried. Now see, it is now okay. So you can see that this f is equal to f of r times r hat, or equivalently you may say that this is f of r times r over r. Okay, in fact you can compare this equation. Let us say this is equation 2 and this is equation 1. Okay, so comparing these two equations, you can see that I have written this f of r at the place of what? This f of r has been written at the place of minus g mm naught over r square. And you can see that this g is a universal constant, m and m naught are given masses, so they are also constant. So this magnitude of this force is only a function of r. Okay, and as I have seen in the definition, that whenever a force f can be expressed by this equation, that is f equal to f of r times r hat, then we say that the force is a central force. And you can see that this gravitational force satisfies this very condition. Okay, and so you can say that gravitational force is a central force. At the same time, you can see that this f of r is negative, that is, this is less than 0, and if it is less than 0, you can say that the gravitational force is an attractive central force. So this is attractive central force. Attractive central force. I hope you have understand that how we can say that gravitational force is a central force, and particularly an attractive central force. Now let us take the another example which is also very important, and the another important example is a electrostatic force. Electrostatic force. You know that the electrostatic force acts between 2 point charges at rest, and this force may be either attractive or repulsive. It is not always attractive, not always repulsive like the gravitational force, but it is either attractive or repulsive. So to know it, let us consider at that point P there is a test charge, let us say Q naught, and this test charge may be either plus or minus. and this at this point O there is another charge, let us say plus minus q. So in this figure I have shown that both of the charges, that is q and q naught, both are of same sign. When you take q naught positive, then q is also positive. If you take q naught negative, then q is also negative. In fact, in this case, the repulsive electrostatic force will act on this q naught. Okay, but situation may be like this. If you consider that at this point P the charge is plus minus q naught, but at the point O the charge is minus plus q. It means the charges q and q naught are of opposite signs. When q naught is positive, in that condition q is negative, and when q naught is negative, then q is positive. Okay, so this is the case of repulsion, that is repulsive electrostatic force will act in this condition. And according to Coulomb's law, the second situation is the case of attraction. Okay, case of attraction. So in this situation, if we consider the situation of this first figure, that is the case of repulsion, then the force acting on q naught due to this q, what will be that? So force acting on plus minus q naught due to plus minus q is given by, this force will be given as F equal to 1 over 4 pi epsilon naught q times q naught over r square. Here actually again you can say that this r is the position vector of point P with respect to O. Okay, r is the position vector of P with respect to O, and times r hat. R hat actually it is the unit vector, in the direction of this radial vector r. Okay, or position vector r. Okay, now you can see that this expression may be equivalently written as F equal to 1 over 4 pi epsilon naught q naught over r square times r by mod of r. Okay, and let us say this is your equation 1. Now compare this equation 1 with this equation, F equal to F of r times r hat, or you can say F of r times r by mod of r. Compare these two. You can see that this expression for the electrostatic force can be written like this, which I have written in equation 2. So here you can say that F of r is equal to what? This is 1 over 4 pi epsilon naught q naught over r square. Okay, and this is greater than 0. So you can see that the expression for the electrostatic force acting on a point charge due to another point charge, which I have defined from Coulomb's law, it follows the same symbol or same condition or same criteria as a central force. And so you can say that electrostatic force is a very good example of a central force, and in this condition, when the two charges are of similar sign, then this force is repulsive. And so this is because this is positive, and this indicates that the force is repulsive. Okay, repulsive force. Now, if you consider the situation which I have shown in the second figure, where I have considered that the charge situated at point P is plus minus Q naught, and at O the charge situated is minus plus Q. It means both of the charges are not of same sign but of opposite sign. So you can say electrostatic force. Electrostatic force on plus minus Q naught due to minus plus Q is given by, this force will be what? This force will be given by minus 1 over 4 pi epsilon naught Q naught over R square times R hat, because in this condition the force will be attractive, and this force on Q naught will act in the decreasing direction of this vector R, and so I have put here the sign of minus. Okay, and again you can see that this F is just equal to F of R times R hat. But what is F of R here? You can see this F of R is equal to minus 1 over 4 pi epsilon naught Q naught over R square, and this is less than 0, that is negative, and this implies that this central force is an attractive central force. Okay, so you can see from this example that the gravitational force and the electrostatic force fulfill all the criteria, all the conditions which is necessary for a force to be a central force. So you can say that the gravitational force and the electrostatic force is are very good examples of central force. And in fact, in the forthcoming lectures, in accordance with our syllabus, we have to study the motion of particles in both of these central force fields. When you will discuss the Rutherford scattering, then we actually study the motion of a charged particle in electrostatic field, and when you study the planetary motion, that is Kepler's law, then you study the motion under the gravitational force. So these two forces are very good examples of central forces, and our study will be actually based on the motion of particles under these two forces in classical mechanics. But in quantum mechanics, when you study quantum mechanics, again the problem on central force field comes, but in quantum mechanics the technique is different, but the idea will remain same. Okay, so this was just an elementary lecture to know what is central force. I hope you have understand it, and in the forthcoming lecture we will see the important characteristics or properties of this central force. Okay.